Welcome back to the Lowdown on Physics. This is screencast 2 for Unit 2 Area of Study 1 Motion. Today we're going to be looking at speed, velocity and acceleration. I want to start off today by looking at speed and contrasting that with velocity and the scalar vector nature of the two and how they differ and what they have in common as well, I suppose. Now, speed is a scalar quantity. It measures the change in distance per unit of time. So it's a rate of change of distance over time. Now, you'll notice here distance is a scalar quantity, time is a scalar quantity, so the result is going to be a scalar quantity. In contrast to that, velocity is a measure of the rate of the displacement. That is a vector quantity, so the result is that velocity is a vector quantity. So it's an average rate of change of displacement with time. Okay, so if we're traveling in a single direction only, the magnitude of this would be the same as it is for speed because the displacement and the distance would be the same. But in contrast, velocity is different when we involve more than one direction, and that's because of the vector nature of displacement compared to distance. If you're not sure what I'm talking about, see screencast 1 for this series. Now, I just want to quickly touch on two different things that can be said about velocity. We've got something called relative velocity, and I suppose that's what we're always measuring. Velocity that we normally talk about is relative to the Earth. We assume that the Earth is stationary, but sometimes we may measure velocity by an observer who's moving, and that's called relative velocity, such as a policeman driving his car who determines the speed of a car that's coming towards him and whether he should or not give him a speeding ticket or not. So it's the difference between the two velocities relative to the ground, which is our overall frame of reference. So basically, can really be summarized in a small equation where we'd say velocity of car 1 relative to car 2 is the difference of velocity of car 1, that's from the frame of reference of the ground, minus velocity of car 2. From the frame of reference being the ground. So for example, we've got car 1 travelling at 20 meters per second north, car 2 is travelling at 20 meters per second south. What's the velocity of car 1 relative to car 2? Well, car 1, 20 meters per second north, if we did it by way of calculation, we'd be saying 20 meters per second north minus 20 meters per second south, which would be 20 meters per second north plus 20 meters per second north. So it would appear from car 2 that car 1 was traveling at 40 meters per second north, or it's disappearing in a northerly direction at 40 meters per second away from car 2. Okay, that gets covered in a bit more detail at Unit 3, but it's kind of good to get your head around a basic understanding now. Another one would be instantaneous speed or instantaneous velocity. And that's the speed that it's traveling at that very instant in time. Usually we do calculations involving average speeds, and obviously the longer the time interval goes, the more variation in speed, the less accurate it is in giving you the current speed that you're traveling at. So instantaneous velocity, obviously it's just the speed or velocity at that very instant in time. Okay, so if it moves at constant velocity, those two things will be the same. If it's varying, so if it's speeding up and slowing down, then it will change. Okay, so speaking of speeding up and slowing down, that brings us to acceleration. Now, acceleration is a word that we're fairly familiar with in the English language, but it's the rate of change of velocity. Now we're talking about the change in velocity per unit time. Velocity is a vector quantity, which means that we now have a vector quantity as a result. Now the effect that the acceleration can have on the object and its velocity is one of three options. It can be in the same direction, therefore it's causing it to speed up. It can be in the opposite direction, causing it to slow down, or it could act at right angles, which is causing it to change direction. The speed would remain the same, but the direction would change. And because velocity has a direction associated with it, it's changing its velocity. Okay, so acceleration in the opposite direction means that it's going to slow down. So negative acceleration, sometimes we call it deceleration, would be negative. Now the average acceleration, assuming that we're undergoing a constant acceleration, we could use this equation here. Change in velocity per unit time. Sometimes we represent that as v minus u, where v is the final velocity and u is the initial velocity. So the difference in the velocities, this is where vector subtraction comes in, over the time. Okay, so we're delta v, change in velocity, delta t, change in time. Now I want to introduce three equations of motion that we use for objects undergoing constant acceleration. So firstly, we've got v equals u plus at. That's actually just a rearrangement of the acceleration equation we had on the previous slide. So a equals v minus u over t, multiply by t, and then add u. We actually rearrange, make v the subject, producing that equation. Other ones are v squared equals u squared plus 2ax. X is displacement, a acceleration, v and u our final and initial velocities, and x equals ut plus a half at squared. Now, pretty much any problem that we get given undergoing constant acceleration, we can get out and resolve with these three equations. So you'll use them a lot, write them somewhere where you can refer to them regularly. So now I want to just touch base on solving problems in physics. You know, the key things that I find help students, and those that consistently do it, consistently get more problems out than those that don't. So first thing is, if you're not given a diagram, draw one. Try and make sense of the information you're given. Secondly, list your variables. That means get the information from the question, write it out. Final velocity, so write v equals 12 meters per second east. A equals 2 meters per second west. You know, write the information that you're given down, and then because you've listed it, after checking that all your units are consistent, so we've got SI units before substituting, you can find the equation which is going to satisfy your variables. So you've listed all your variables, including the one you're after, so that you can then look at it and then pick the appropriate equation to solve. So then you substitute in and solve for whatever the unknown is that you were looking for. So those that draw diagrams, list variables, and then substitute in tend, in my experience, to do better than those that don't. So really good habit to get into. So last thing I just want to work through is a very quick example. Find the acceleration of a car. We've got initial velocity is 12 meters per second west. Final velocity is 5 meters per second east. And it's accelerated, that change occurred in 4 seconds. So we're after A equals V minus U over T. The important thing here, final velocity 5 meters per second east. We've got 12 meters per second west as our initial velocity. So I'm going to write that as negative 12 meters per second east. Now we're all in the same direction. It's a bit easier to deal with. So when I substitute that in, I've got 5 east minus negative 12 east over 4, which gives me an acceleration of 4.25 meters per second squared, and that's in the east direction. I know it's east because my answer has come out positive. So we'll look at more examples and practice that in class. So I'll see you then.